NVIDIA. I was a research scientist for about 3 years at IBM Quantum, working on bringing up some of the quantum systems there. I did some benchmarking of the quantum systems as well as some algorithms and applications experiments there. So I did my PhD prior to that at Princeton, looking at single electron spins for use as qubits. So at NVIDIA today, we've developed a few simulation tools and products where our goal here is to essentially enable the entire quantum ecosystem with the most performant simulation tools. So of course, quantum computers today are still emerging, and what we're trying to do is enable novel algorithms and applications research with the best classical tools, including HPC resources. So I'm joined by my colleagues here today, Dave Fisk, Jonathan Dursey, and Filippo Spiga, who will be helping present on cuQuantum, our SDK for accelerating quantum circuit simulation. And we'll be walking you through to some of the tools that have really enabled some massive speedups of quantum circuit simulation using NVIDIA GPU tools. So thanks again for attending. And at this point, I'll turn it over to Dave Fisk. Thanks.
Thanks, Jen. Welcome, everyone. I'm a solutions architect for NVIDIA supporting Google Cloud primarily, and I'm mostly in full stack end-to-end performance engineering, troubleshooting, and so forth. But I've stepped up here out of an abundance of interest to help out with the presentation here today, and I've been working to prove out scalability in the cloud and working with the libraries, just part of the overall effort to get familiar with and help promote the technology here. So without further ado, we'll jump right in here and get started. And let me see here. Another day, another conference interface. Let me figure out my sharing here. We'll be starting momentarily. Okay. Do you see the screen?
Looks good.
Yes. All right. So welcome, and let's get right into it. Today we're going to present an overview of quantum computing and the cuQuantum acceleration libraries NVIDIA has to help accelerate quantum simulation. Then we have 3 labs planned. So this is the overview. And to dive right in, quantum computing is a new paradigm in computing that has the potential for exceeding the compute capability of classical computers in a tremendous way. That is, problems that are intractable in a classical computing model become approachable in quantum computing. This is the long-term promise or interest in quantum computing, is to identify and realize this quantum advantage. So we're in the early stages of this, and there's a lot of excitement around it. So this picture we're showing here on the left is a common picture you've probably seen when we talk about quantum computers. Everyone likes to show this picture. It's rather beautiful. The mass majority of what you're seeing in that image is not the actual quantum computer. It's this little device in the very bottom here is the actual Sycamore processor. This is the Google's quantum computer, and everything you see here is the refrigeration unit. This is a superconducting approach to creating quantum computing, and it's largely about bringing the temperature to near zero for the superconductors to operate. So almost everything you see here is part of the refrigeration unit with the quantum device there. But the quantum computing is different than classical computing in the sense that we now represent information not by a single bit with a 0 or 1, but take advantage of the quantum principles of superposition and entanglement, represent information as a 0 and 1 simultaneously. That is, a bit is in a superposition of being either a 0 or 1, and the actual value only comes out on measurement. We'll get into that a little bit more later and describe some of the information around that. But there are both near-term and far-term potentials here that are interesting. In the far term, we do have a couple of examples now proven mathematically and rigorously where there is a quantum advantage that allows this tremendous improvement in capability in computation. So the near-term potential then is, it's a long way off though, but the problem with the proven algorithms, Shor's and Grover's, and we'll talk about that in a little more detail now, prime number factorization has huge implications for cryptography, which got everyone's interest. And for example, the Sycamore supremacy claim of Google, some early work that they did, not necessarily an interesting, a useful algorithm, but a proof of the calculation comparison, and has an example that shows a quantum computation taking on the order of 200 seconds that it was estimated and claimed by Google from their analysis would take on the order of 10,000 years to do on a classical computing device. So that gives you a notion of the scale of the potential here. And there are these two algorithms that we'll talk about. There are several others, but the two that we often talk about are Shor's algorithm and Grover's algorithm, and they will require a large number of physical bits in the hardware in order to achieve this computational advantage, and we're a ways off from that. So it's estimated that we're going to need on the order of 1 million physical qubits in order to have enough usable fault-tolerant qubits to do the actual work. So the current state of the art with the hardware is it's very noisy. There's high error rates, so there's a need for a large number of physical qubits in order to have error handling and to create a fault tolerant computing environment to realize the computational advantage. As you might imagine, potential use cases, finance, fortunes are made and lost based on seconds of analysis in the world's markets. So any kind of computational advantage to driving finance is, of course, of interest. Healthcare, quantum chemistry, the potential for finding new drug discovery. Cryptography has everyone, of course, it's one of the canonical cases for quantum computing where everyone's a little concerned that by the time we have a large enough quantum computer, our 2048-bit RSA encryption is no longer safe. No immediate panic. It's going to be a while, but you can see we're probably going to need quantum encryption to deal with the ability of quantum computers to break encryption, right? So it's a whole new world of cryptography is implied by this compute capability. And then lastly, all areas of optimization. Quantum algorithms and quantum computing would seem particularly well suited for optimization problems in general. The mathematics involved is very much in the neighborhood of what we're used to seeing over the years with min-max optimization theorems, the complementary slackness, the whole mathematical apparatus of optimization and minimization, projecting forms into higher dimensional spaces. All of this happens very naturally in quantum mechanics through the sort of linear operators in Hilbert space on which the mathematics is based. So the far-term applications, and these are the ones that we have proven mathematical, we have proofs that this quantum advantage really does exist. But the downside is, or the barrier, if you will, is it's going to take 1 million physical qubits to realize this, and it's a ways off, as we were discussing in the previous slide. But we do know that there's an exponential speed up in computational ability here, given the Shor's algorithm implemented as a quantum circuit, as a quantum program, and that's got a lot of folks interested. In the United States, the White House just issued an update to their memorandum on quantum computing initiative specifically for this. I think there's some 20 or so initiatives, and something like 70% of companies have some kind of quantum initiative. There's a tremendous amount of interest in the space because of the potential far-reaching implications of Shor's algorithm in particular. Another example of a proven far-term quantum advantage is Grover's algorithm, which is a brute force quadratic speedup of what would be a linear search in classical computing. So as you can see in this illustration here, if you're looking to find a number in a series of numbers, it's just a sequential, a linear search is pretty much what you've got to work with. So with you're looking at a linear complexity and linear computational approach there. But in quantum mechanics, with exploiting the algorithm, exploiting entanglement and qubits, there's something, a technique called amplitude amplification. We're able to have a brute force, just off the shelf quadratic speed up of what would otherwise be a linear search. So these are two examples of far-reaching applications that is a far a ways off, but we know mathematically they're proven that the quantum advantage exists, and that these are the couple of the the real motivators to getting people excited about finding these optimal algorithms and producing the hardware to actually realize this quantum advantage. So let's talk a little bit more in detail about the kinds of things people are investigating, where the research is. And again, these are not proven. The near term, a lot of where the interest is today is what can we do sooner than later? Where can we find quantum advantage where it's not a given that any and every algorithm can be solved better in quantum computing. The expectation is there are going to be these cases where we have these kind of breakthroughs where we have we realize the quantum advantage for a given problem. So the research is on. It's not. It's an area of active research. This near-term potential is to be proven, and these are some of the areas where people are expending a lot of their current efforts to look for opportunity to find this quantum advantage. On the left here, we're showing some of the for chemistry, material science, drug discovery. Again, the quantum computers are really good at doing quantum algorithms. It makes sense, and matter is quantum mechanical, right? So when you zoom down to the level of molecular and atomic level of granularity, things behave quantum mechanically, and a lot of the problems that we're interested in solving live in this space. So it makes sense that quantum computing would have an advantage here to simulate and to run, to calculate, to model these world physical phenomenon. An example of the magnitude of the kind of benefit that is possible, we like to point to this one example because it shows the impact that a solution in these spaces could bring to the world. That molecule that we're showing there, that's a ammonia. And we like to point to this example because it's one of the most significant problems that was ever solved, and that you could pretty much attribute modern civilization to this one technique or discovery. It's the Haber-Bosch process whereby nitrogen is extracted from the air and combined with hydrogen, mostly from methane, with enormous amount of pressure and heat to produce ammonia. And that is pretty much responsible for civilization as we know it today, because that's where our fertilizer comes from to grow crops at the scale that we kind of take for granted in today's society. But it really was an enormous technological breakthrough that allowed that to happen. And that's the kind of magnitude of scale, like the killer app, right? If you can find these kind of solutions in these other spaces to make those kind of contributions, is what everyone's so excited about with the new capability that we have and potential that we have in quantum computing, and in particular the quantum advantage that we're looking for here. Some other examples: battery technology is ripe for innovation, and just in terms of its importance, any advancements we can make in our battery technology to help promote energy sustainability is going to be an important contribution moving forward. So there's a lot of interest in developing new solutions in that space. And last but not least in this area, protein folding. Ground state, determining the ground state energy of a system is one of the keys to doing protein folding calculations, and then calculating how this protein is going to fold up on itself and the shapes that it forms is really critical for drug discovery and working with the chemistry applications for molecular biology and so forth. Moving over to finance logistics, it's not hard to imagine the impact of being able to optimize better a lot of these are NP complete, like the traveling salesman problem. There are a lot of very difficult problems in getting logistics right in managing world supply chain. Anything that we can do to improve that has huge implications. Again, as far as the potential benefits, leading back to the other example, that ammonia process, creating ammonia from nitrogen in the air, and that whole process consumes something like 2%. It's like 2% of the global carbon footprint and energy usage. So again, anything we can do to reduce that energy requirement. Bouncing around machine learning, one of the primary activities in quantum computing is something called the Hamiltonian. The collapse of the wave function involves the system becoming an eigenstate of the observable. So these linear operators in Hilbert space, and the mathematics of this is very similar to a cost minimization optimization problem. Intuitively, you can understand it a lot, the geometry of like a linear program and simplex method and these sort of convex sets very naturally lends itself to the sort of again, like projecting dimensions into higher spaces and working with the geometrical interpretation of cosines as probability amplitudes. All of the mathematics around that is just a natural fit for optimization. So the kind of problems we solve with deep neural networks and training networks and all these sort of very much matrix intense operations for vector state support machines and so on are a natural fit for quantum algorithms and quantum computing. So there's a lot of interest in exploring these areas. And here we just have an assortment of some additional potential applications here. Against quantum support vector machines, very much a natural fit for quantum algorithms in general. Quantum chemistry, again, combinatorial optimization. These large network sort of convex set mathematical optimization problems are ripe for exploration and being represented and solved, and potentially reveal this quantum advantage we're looking for in the near term. So let's talk a little bit about how does this work? What's different? What is a qubit? So traditionally, we represent a bit as a 0 or a 1, and in quantum computing now we're talking about a superposition of a 0 or 1, and these are complex coefficients. This whole mathematical environment is a complex space, Hilbert space, and so you have two coefficients for every bit instead of one, and they're complex. So there are four floating point values, to represent a qubit. And then the principles of superposition are that a good example, a way to think of it is take a coin and spin it on the edge of a table. Is it a heads or a tails, right? Until you slap it and stop it, or you stop the spin, you measure it, you're going to get a heads or a tails. But while the coin is spinning on its side, it's in a and now, like, it's a good way to visualize this idea of superposition. It's both a 0 and 1. It's neither a 0 or 1 until you measure it, and you definitely have a 0 or a 1 or a heads or a tails. So that's the superposition principle. The other principle that allows quantum computing in this ripe area for exploration is the entanglement. And this is really the secret sauce, where when you measure a qubit, you're going to get a value based on the probabilistic state space. So if it's heads or tails, right, you've got a 50-50 chance every time you measure it. But when qubits are entangled, 100% of the time you have correlation. So it's either going to be an exact correlation or an inverse correlation. If these qubits are entangled and I measure this one and it's a 1, then I immediately know all the others are 1s or 0s, depending on the kind of entanglement that's involved. So you can imagine this sort of instantaneous knowledge across a large number of entangled bits of information is the cutting edge of the secret sauce of how do we exploit this in these massively parallel computations, and being able to take exponential complexity and reduce it to polynomial complexity by taking advantage of these principles. But the problem now in representing this in classical computers is we have a power set relationship here. The state space in this particular approach of state space quantum simulation, you have a doubling of memory every time you add a qubit. And so not hard to imagine this gets to be a limiting factor pretty quickly. So anytime you're exponential, you've got a problem, right? There's a term for that, right? The exponential hell or something. I forget what it's called. The exponential catastrophe or something. Things get too big to become intractable in terms of memory requirements. So this is a big limiting factor today for what we can do in a simulation of a large number of qubits is just the memory requirement. Again, doubling the memory requirement as you add each qubits. So, and there's a trade-off between the different approaches that we'll talk about a little bit more, that how do you capture quantum effects and create a quantum computer from those effects. There are different approaches. They have trade-offs largely in this area of how many qubits can you represent and what's the coherence of those qubits. This entanglement state it degrades over time, right? There's it's in the order of hundreds of microseconds, excuse me, for current for a superconductor type quantum machine. The coherence of the entanglement is on the order of 100 milliseconds. So these things have to be used readily, right? There's not a long persistence today, but you can represent a fairly deep entangled state. But you only have, I think, on the order of like the Sycamore machine is 53 bits. I think it's a 54-bit machine. One of them didn't come out right. So 53 hard bits. In the simulations, we're able to get into the with this sort of a state space simulations. I think on the order of in the low hundreds of qubits. More, and on some of my own personal working with machines, some of the largest machines I've been work with in Google Cloud, for example, we can get 36 qubits on a 16A100 shape. So it takes a lot of hardware to start approaching these higher orders of qubit. And that's the problem with this 2 to the n power set. It's really representing every possible state of every permutation state. If you take 2 to the n, the power set, that's the state space that's being represented, and there's a probability for every state that then obtains when you take the measurement. So the way that this is programmed looks a lot like a conventional electrical circuit. That's why we call them quantum circuits. But it's important to realize this is a program, and this is how you program a quantum computer. It's this quantum circuit idea. So on the left, you see a classical circuit where each of the wires would represent a single bit. And on the right, you see a quantum circuit where each wire represents a qubit. And these single operator gates here are a single qubit operation on a gate, the Hammond gate there. And then these hatched ones that are showing entangling bits, where you have a conditional operation on a bit that ends up entangling those bits. So this gets represented in these are called Bosch spheres, which are a nice visual way to understand this superposition of being either 0 or 1. Anywhere on the surface of that sphere is a pure state. You're some linear combination of 0 and 1. Until you take the measurements, it's always a discrete 0 or 1. And if you were to be inside that sphere, it gets into something called mixed states, which is something different altogether. But you can think of this being the superposition state being is on the surface of that sphere until you make the measurement. And this entanglement then leads you to the situation where, regardless of the probabilities of the measurement, you get, again, you're going to have a probabilistic outcome when you take the measurement, but it's 100% correlation for the entangled bits. And that's really the power and the secret sauce of this quantum entanglement principle as it's being leveraged in these quantum algorithms to, again, seeking to find this advantage that this whole approach can bring over classical computing and exploit the inherent parallelism of this entanglement process. So let's talk a little bit about how this actually gets implemented today. There's a number of research areas of how to do this physically. Some of the more popular and the machine that we were looking at the pictures of, this refrigerated, this near absolute zero superconducting approach, where you have essentially quantum tunneling happening between the superconductors in the device itself. All of these principles, all of these approaches in some way or another look to isolate and trap some measurable properties of quantum particles that can be used to make these measurements. It could be the spin of electron or the polarity of a photon. These are the kind of physical properties that we're using to represent a qubit. And the superconductor principle, as I mentioned, it's near absolute zero electrical circuits, currents going through electrical coils that the frequency and the fluctuation of the frequency produces, and quantum tunneling between them is able to isolate and have a measurable difference in ground states and excitement state that effectively represents zeros or ones. It's essentially along those lines. Some other principles, or the beauty of this is you can represent really deeply entangled states, but you have limitations. Again, the memory requirements and the let me see the coherence of the bits. Again, along the order of 100 microseconds. So some of the trade-offs there is what the coherence times versus how deep, how entangled a system that you can represent. This is full state, kind of brute force, really. This, if you're doing the full state simulation. But some other approaches, ion traps. This is using ionized gas with lasers. The ways of isolating, again, getting some approach to being able to isolate particles and be able to get a quantum measurement of spin, or again with the silicon photonics. There's taking the advantage of some of the infrastructure for producing silicon in general, silicon waveguides. There's a way to encode the materials so that you can use the polarity of the light in the material as a quantum bit. Let me see. There's other approaches: neutral atoms versus ions, quantum dots, topological qubits, diamond vacancies, which have the advantage of potentially operating at room temperature. Some of these can represent much larger numbers of qubits, but with less entanglement. So there are various trade-offs, and again, an area of just active research in identifying materials, the material science of this, and the techniques and environments that can maintain this quantum state for longer periods and be able to support the actual computation through these principles. So where are we today, and where is all this going? We're currently in this period of time referred to as NISQ, that noisy intermediate scale quantum era. And so we have some tangible proof of the quantum advantage, the Shor's and Grover's algorithms, that we have proofs that we know that there's this advantage, this computational advantage is available, and we have some hardware where we're demonstrating some real physical capabilities. The supremacy, the Sycamore supremacy circuit, for example, where this 200 seconds versus 10,000 years kind of capability. But currently these systems are very noisy. There are high error rates. And that's, again, we're going to need 1 million physical qubits before we have enough ones that are reliable enough to do fault tolerant computing with these principles, which is that where we're shooting for. And to get there, even by the mid-century, as you can see in this chart here, it's estimated we're going to like double capability, every year or so, to get whatever that trajectory is there, to get us from, on the order of 100 qubits, and to over 1 million by, say, 2040. But in the meantime, so we have this long-term potential of quantum advantage. There's plenty of reason to be excited about it. No one knows for sure how long it will take to get there, or if we'll even get there. It's really not proven, but it seems very likely, given the amount of the results that we've seen so far, and the amount of energy and effort that's going into proving out these and developing these systems, would imply that we're going to get there. And again, the race is sort of on to figure out, what are going to be those algorithms that we can bring to bear, then really take the quantum advantage to make the world a better place in no small way. Some of the breakthroughs that are possible and that we're looking for over the long run here. But again, today it's very noisy. It takes a large number of real qubits to realize the advantage we know is possible. So in the near term, it's about discovering what are the other possible, perhaps sooner than later, quantum advantages that can be realized. And so it's kind of where we are today. And that brings us to the near term. What can we do? And before we have these sort of large scale physical systems is to simulate them. And that's where brings us to NVIDIA's contribution in this field. There are two areas where NVIDIA is focused on helping promote and support this research. One is in accelerating the quantum circuit simulation itself, and the other is building the tool chains to support this ultimate, what we expect to be a hybrid classical quantum computer. So you can think of it as the quantum processing unit, the QPU, is the likely way in which this compute capability will be brought to bear as it becomes mature. So the tool chain for supporting that, and what does that look like, and something NVIDIA has a lot of experience with. So it's very similar to the approach that we take with GPU and massively parallel computing today and classical supercomputers, but introducing this new compute capability as part of that overall infrastructure. But a lot of the same considerations in terms of the development and deployment environment and how you work with this stuff on a day-to-day basis when it really becomes operationalized is one of the areas NVIDIA is focused on. And of course, what NVIDIA traditionally does best too is just massively parallel acceleration of computational tasks involving lots of matrix operations. And as you probably can tell, that's a lot of what's going on here. So solving these state models and are largely just very, very high requirements of floating point operations to do those calculations, and to accelerate them and doing them in parallel is the best we can do today with today's technology. And that's what we've pretty much focused on at NVIDIA. So there are two main approaches then to solving these problems and to doing a quantum circuit simulation. The brute force approach is state vector simulation, is the full power set 2 to the n, every possible state of the system. You're calculating a probability, the entire state space is there. And this is very effective, complete, however, has this problem, this exponential memory requirement for the simulation. So we're limited to about 50 qubits today on a supercomputer using this approach. And this is fully supported by cuQuantum accelerator that NVIDIA is bringing to bear here. It has these two primary acceleration entry points: the state vector simulation, Q state vector, and Q TensorNet for the tensor networks. The tensor networks, on the other hand, are a different approach. It's more like a sparse approach to focusing on just what you need to know. Being able to limit the memory requirements by focusing the problem and finding the optimal contraction paths through the representation. And there are tools in the cuQuantum library as well to let you convert your circuits from a Qiskit, which is IBM's package, or CirQ, QSIM from Google. There's Penny Lanes from Zandu. They're the primary platforms that we're integrated with today, but the NVIDIA acceleration libraries are agnostic with respect to the simulation tool. It's not a simulator, it's a low-level API for plugging into these simulation libraries that can then accelerate the actual computations, which is what GPUs do best. So we'll talk a little bit more about this and how they're used, and we get a chance to work with these in the tutorials coming up here. One of the big trade-offs here too, when you go from a state vector simulation to this tensor network approach, is you have more limits. You're more limited in terms of how deep and how entangled the networks you can represent effectively, but it opens up the number of qubits that can effectively be simulated. So into the thousands of qubits are possible with this approach. So it gets around the exponential memory problem. And so these are the two primary approaches, and both lend themselves very well to GPU acceleration. So looking at a little bit of where we are today in terms of the overlap of these two approaches and the kind of problems you can solve with them. As you can see, the two vertical red lines here show us our the exponential memory requirement, where that leaves us in terms of for all practicality, the largest memory systems available to do these sort of simulations on a supercomputer today, versus being able to represent these circuits as tensor networks and solve them through this other tensor network approach. So let's give you an idea of the circuit depth versus the amount of memory, the memory requirement, and some overlap between these two approaches is kind of where we are today. And we do have some breakthroughs we'll talk about here in a little bit, demonstrating the effectiveness of these approaches for the max cut problem in particular. We've had a recent pretty significant breakthrough in demonstrating the effectiveness of this approach for solving real problems. So these acceleration, the Q state vector, Q TensorNet accelerations are provided in the cuQuantum library, and then they are transparent to you. They plug in at the library level underneath the platform layers, so that whether you're using a Circu or Qiskit or the Xandu Penny Lane, they plug in at the library level. You needn't nothing changes in terms of how you use the libraries. It's just an acceleration that happens at the lower level, at the library level, for making these things run faster, simply just doing the calculations on GPU instead of CPU. And we're seeing on the order of anywhere from order of magnitude to a couple orders of magnitude improvement, as we're not we're kind of used to seeing that, right? If you comparing CPU to GPU, it's possible to get 20x, 24, 30x speed up is not that uncommon, really. So we have this massively parallel compute capability for classical computing that we can plug in to make these quantum simulations much more performant and allow the researchers to iterate. But this is the overall model we're shooting for. And again, kind of depicted here is this ultimate sort of hybrid environment where you have the QPU to plug into this when you actually have the physical hardware. But in the meantime, a lot of the importance of understanding how these algorithms work and developing them and improving them out now versus when the physical hardware is available is supported by the simulation approach. And that's where cuQuantum comes in to make that available to you. And that's what we'll be playing with here in the tutorials today, running through some examples and see how easy it is to get up and running with these libraries. I should mention too, just because it's close to me personally, and I just wanted to share it with you, we have something called the HPC Toolkit available at Google. With a single line of Terraform, you can stand up a machine image with the cuQuantum QCirc with Google's stuff, and then a couple other commands. Download the NVIDIA container. We have the cuQuantum has a appliance, the DGX appliance, and you can have all of this stuff and be up and running, inside of minutes, really. So there's a lot of support for getting you into an environment in the cloud in particular. So the barrier to entry is very low to get started, and you can be you can be working with this stuff pretty easily. A little overview of the who's who in the cuQuantum ecosystem here. Pretty much a lot of attention from all the top players because the implications are just enormous. So no small turnout for the research party here. Everyone's taking a pretty serious look at this stuff, and it's all really very exciting, I think, to see where this is going. Some of the main platforms, and again, the effect of speeding this stuff up with cuQuantum performance, having some really good results there. So again, all of this coming together to make this research really doable, right? We're in a position where you can do a lot of iteration. You can have some really quick turnarounds in this work and have a very performant simulation environment to do this kind of research. Looking at some specifics here. This is a quantum Fourier transform Shor's algorithm, the Sycamore supremacy circuit, which is the one that, again, whether it's actually useful or not, I think it's more of a demonstration of compute complexity and comparing classical to quantum computing, where we have that 200 seconds versus 10,000 years kind of differential that has got us all, pretty interested. But comparing these to the number of qubits and what the kind of speed up we're seeing with the cuQuantum acceleration today, again, on the order of a couple of orders of magnitude speed up, you can appreciate there. And those variational quantum eigenstate finders here, with 22 bits, the 18x speed up. Again, just short of an order of magnitude here. But pretty nice results there for accelerating these libraries. Penny Lane. This is the machine learning libraries for cuQuantum, quantum machine learning, and again, about an order of magnitude speed up using the cuQuantum acceleration for Penny Lane. And strong scalability. This is demonstrated on a DGX, which is a tightly integrated NVLink supported eight GPUs working in tightly coupled in a single machine, and where we're getting really nice strong scalability for these algorithms as well. So some examples now, moving on, some recent breakthroughs wanted to share, in particular a little bit of the results that we're getting applying this stuff. The CU TensorNet that we talked about before, the approach that it takes to making these problems more tractable and to allow more qubits to be represented is to find an optimal path for contraction. And here it's showing an example whereby, in mathematics and matrix representation in particular, there's many different ways you can represent a fundamentally equivalent mathematical object representation, right? Effectively, every matrix representation has a canonical eigenstate form where you can have all the values or eigenvalues on the diagonal, which is equivalent to endlessly other representations, right? So there's a lot of flexibility in how you can represent the same state, basically, and exploiting that to find optimal ways to reduce the number of floating point operations to arrive at the same answer. Basically, the order, it's not unlike the kind of database optimization planning like Corey plans. Is that kind of an approach where you're, instead of just brute force jumping in and solving the doing the calculations as presented, it's looking for a way to simplify the problem, the approach to the order of operations, to refactor it, to arrive at a representation, an equivalent representation, which lends itself to a much less complexity. So in this example, we have, for example, cubic complexity reduced to linear. So just just n versus n to the n cubed in terms of complexity by doing an order of reduction order by one here. So pulling out the n, one of the n's, and refactoring this equivalent system, but ultimately making the contraction path that much less compute intensive. So that's the basic idea. This CU TensorNet allows much more difficult problems to be solved by finding a way to an equivalent representation that then is much more tractable on our given resources today. So this is the basic approach to that. There's an optimization phase, finding the optimal path, and then actually executing it. And this is, active research. There's a lot going on here, in terms of acceleration. As you can see, it's not just plugging in GPUs to do the calculation. It's this optimization software approach to just putting a lot of smarts into how you go about doing the work to be as efficient as possible. So this gives you an idea of what's going on under the covers there, as it looks to find these reduced complexity, optimal computation paths for contracting tensor networks. Again, just some more pictorial examples of how that works. So it's all about just reducing the computational complexity and then executing it. And there's other interesting things going on there too. You want to spend too much time trying to find the optimal path, right? That's latency as well. How much time do you spend searching for an optimal path versus how much time do you spend executing it? So there's a nice balance here between finding a reasonable optimal path and then getting it computed. And again, these sort of equivalent representations that lend themselves to a less complex computational path for doing the contractions. It's a little more detail about the approaches there. And pulling out one of the vertices, and again, the similar kind of refactoring, just refactoring the system is the overall approach here, but variations on that theme. So a lot of detail here, but again, I keep repeating myself, but we're just reiterating the same basic principle here. Is we're refactoring these networks into an equivalent network that is less computationally intensive. And looking at some of the results of this now compared to some of the other leading techniques and packages available, we're getting over here like 730 times more like speed up there over other approaches to doing the same, to realizing the same contraction. So recently, NVIDIA researchers were able to present a demonstration of using this library and these approaches to solve one of the notoriously difficult problems in classical computing, this max cut problem, where the idea is to find a boundary around some number of vertices such that you have one vertex in and one vertex on the outside of that boundary. So an arbitrary boundary that basically maximizes the number of edges that have one vertex in each of the inside and outside of that boundary. So it's a very computationally intense, NP-complete, hard problem, NP-hard, NP-complete complexity. So a non-polynomial problem. And there's been various approaches to how to solve this in a again, looking for the quantum advantage. We have an example of solving this that NVIDIA researchers submitted here recently of using the max cut problem encoded as a quantum circuit, and we're able to solve this problem at a heretofore unseen scale by running it on NVIDIA's Selene supercomputer and scaled it up to 10,000 vertex count, and this had never been solved at this scale before. So this is, using this quantum circuit to solve this problem on a simulator and being able to handle it up to 10,000 vertices. And it wasn't even done yet. This was on a 20 node system, and there's room to grow this even more. But even at this scale, that has never been demonstrated at this level before. So there's a pretty exciting result. So we're seeing this stuff is panning out in terms of its effectiveness, and the future looks bright for applying these technologies to the problem of discovering quantum advantage through algorithms that exploit superposition and entanglement to deliver this enormous compute capability. So in summary, just like to invite everyone to get excited about this technology, and to glad you're here today to get familiar with it, and hope, who knows, maybe some of you can help. We'll be the ones to help come up with that killer next algorithm, right? The race is on, and it's really an exciting time in terms of we're at the infancies. Really, we're really in the early stages of this technology, and the potential is just enormous. So it's a very exciting time indeed. So with that, I think we're ready to roll up our sleeves and get our hands dirty and start working with the APIs a little bit and use the libraries. I guess any questions, or we can take a brief pause there we move on to the tutorial section. There's some other notes here about the, just wanted to bring this to your attention as well too. You might want to grab a shot of that that URL from the QR code there. Okay, so now we're on to the tutorials. And I'm not really sure about does everyone have their own lab setup here? I'm not real clear on what the logistics of everyone having the tutorials. I can certainly walk through it on my setup, but does everyone have a
They don't, Dave. We're gonna.
They don't. Oh, so I'm just gonna walk through it. Okay.
If you want to take lab 1, I'm happy to take lab 2 and 3.
Sounds good. Okay. So let me get back to sharing again. See if that. And I am still sharing my screen. So I got my multi-monitor set up here, and it likes to hide the controls when you're sharing, so it gets a little dicey. So is that, you're seeing my notebook there?
We are.
Good. Okay, so this is the, if you download the, I guess, does everyone have this available? I guess I showed you the QR code from before. Did everyone get a chance to maybe grab that? So you get access to these notebooks. And again, we'll just kind of walk right through this. It's a Jupyter notebook, which you're probably all quite familiar with. So we're just going to walk right through it here. This is the cuQuantum appliance. It's working with Google's Circuit. And we'll just do some initial examples here. I'll just walk right through it. I'll just kind of read it as we go here. So like just kind of import Circuit and QSIM Circuit. These are the two main imports there. And the first example we're going to look at here is a entanglement of 5 qubits called a GHZ state. So we just create a circuit to get the initial circuit qubits. We can arrange 5. There are a number of ways to create the number of qubits. Here we're just asking for 5 qubits. Again, there's a variety of ways that you can define the qubit layout that you have there. So this is the initial creation of the circuit here. So we're doing this a Hadamard gate and then C0 gates to do the entanglement. So we're initially going to do the qubit 0 and then do this sort of lattice of C0 conditions across those to create the entanglement. And this is the output, how we represent the quantum program, which again looks like a conventional electric circuit diagram, but it's actually a quantum program. Then we get down here and create a simulator. So now we have a circuit and we want to simulate it. So Circuit simulator gives me a simulator handle. So now we're going to do a measurement. And as you can see, we've got a 50-50 chance of having 0 or 1s, but 100% of the time we agree. And that's the entanglement principle that's kind of got us all excited here. So we'll go on to a next example here. This is a building block of mini quantum algorithms, the quantum Fourier transform, QFT. We'll demonstrate that. Create a new circuit here. Hit a simulator. This is how you configure the number of GPUs. We're just running a single on a single V100 here. So these are the main interface points for controlling your number of GPUs and whether you're using GPU or not. So that's as far as integrating the cuQuantum library. It's that simple, really. You just turn on the GPU support with this structure and your QSIM options there. And so we're crunching that now. Okay, runtime is 6 seconds, and that's our quantum Fourier transform representation. So we're going to go on to another example of Shor's algorithm here. This is another example, Shor's algorithm of the prime number factorization. So we'll go on and bring that in. This is using Qiskit, so IBM's quantum computing platform. Pretty nice meaty code here for examples of actually implementing this algorithm. Here's the actual Shor's algorithm itself. So we're going to compare the classical to Shor's here. So here's the classical approach. And it factored it. So we have a factorization. So again, not spectacular in terms of the magnitude of the scale here or the timing of it, but you can just see all the stuff working, and indeed we get our factorization answers correctly. These are some things I added. They're just looking at the versions of Qiskit I had there. But that's the first lab, just walking through the first lab there. But you can see this stuff is really pretty easy to use, and you can get up and running quickly too as far as standing up an environment. So the cuQuantum container from NGC is available, so you can, it's a Linux-based Docker container, so anywhere you have a workstation, it's easy enough to get to be up and running really pretty quickly. Just get the NGC container for cuQuantum, and you have this environment ready to go. So I think with that, we're ready for like some questions, or to take a bit of a break and come back with walk through a couple more tutorials.